and I'll show you what the parent function looks like. So we've already defined a rational function, ratio of two polynomials. The parent function, 1 over x, is what's called a hyperbola. And the graph is two curves that have an asymptote along each of the axes, the x and the y-axis. An asymptote, which is the next vocab word, is a line that a graph approaches but never crosses. So as you can kind of see from my rough sketch here, both, sorry, it's hard for me to do this when you can't watch where I'm pointing. Both of these graphs, as you can see, get very close to the x-axis, but the further you go towards each end, positive or negative infinity, it will never actually touch 0. And same for as it's increasing here, and I just drew that right over, it's approaching the y-axis, but it will never touch it. So in the case of the parent function, the vertical axis obviously is the y-axis, and this occurs when the denominator is 0. So if the function is undefined, and that's what we've been looking at the last several days, is those domain restrictions, that will give us a vertical asymptote. Horizontal asymptotes are a bit more challenging to find. So this is in your book in section 8.4. I apologize I don't have the page number, but you may not want to copy all of this down. It is on a later slide as well when we find horizontal asymptotes. I pasted this on the page as well. A little bit bigger, hopefully a little more clear to read. So what it says is let f of x equal p of x over q of x, where p and q are polynomial functions in standard form with no common factors. So you've already canceled out any common factors, numerator and denominator, and you've simplified the function if you can. The graph of f has at most one horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0, or the x-axis. So that was the same as in our parent function. The x-axis was a horizontal asymptote. And the degree of the parent function in the numerator, remember the parent function was 1 over x, so the degree of the numerator is 0 because there is no variable, and the degree of the denominator is 1. So the degree of the numerator is less, so the x-axis is a horizontal asymptote. And then finally, if the degrees are equal in the numerator and the denominator, the horizontal asymptote is the line y equals the leading coefficient of p over the leading coefficient of q. So we'll see what that looks like a little bit later. And then finally, graphs can also have a hole in them if both the numerator and the denominator equals 0. So if they do have a common factor, then there will be a hole in the graph as opposed to an asymptote. And it's simply a spot that the graph jumps over. All right, so first let's take a look for any vertical asymptotes. We're going to find the domain, which we've been doing, zeros, and the vertical asymptote. So if you look at A, remember the restricted domain, in this case it's going to be the same as the vertical asymptote. The graph, this function, 2x plus 1 over x minus 9, is simplified. There's no factoring I can do, there's no canceling. So in the denominator, our restricted domain is x cannot equal 9. So our vertical asymptote is the line x equals 9. And then the zeros of the function occur when the numerator is 0. So we set the numerator equal to 0. Let me label my work here. So the numerator equal to 0, subtract 1, divide by 2. And that's where our graph, remember that's where the graph crosses the x-axis. Those are the zeros. So this is, again, putting some information together for if we were going to sketch these. All right, so example B, again, we want to find that restricted domain, so that's where the denominator equals 0. In this case, x squared equals 0, or x cannot equal 0. So our vertical asymptote would be the line x equals 0. And then to find the zeros, we set the numerator equal to 0. So on this one, I'm going to add 5 and divide by 2. So I have x cubed equals 5 halves. Now with square roots, when you take a square root, it's positive or negative. When you take a cube root, It's just positive because a number times itself, if you start with a negative, you'll end up with a negative. So this is just, we're gonna simplify it as the cube root of 5/2. And again, that's where the graph crosses the x-axis. Finally, our last example, so our restricted domain is where the denominator equals 0. And this one can be factored. It's the difference of squares. So we have two values that our x cannot equal, which means we have two vertical asymptotes as well. So our asymptotes are x equals 1 and x equals -1. Those are the equations. And then finally the zeros, where the graph crosses the x-axis. Set your numerator equal to 0, so x equals 0. All right, next piece, we're going to take a look at those horizontal asymptotes. So here's that same chart that I had on your vocab sheet, still a little blurry. So what we need to look for is the degree of the numerator and the degree of the denominator. So in this case, the degree of my numerator is 0 because I don't have any variables. The degree of my denominator is 1, x to the first power, and if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Sorry, I was thinking about that and that didn't make sense. The degree of my numerator is not greater than the degree of my denominator. Sorry about that. I was thinking about the parent function and going, wait a minute, the parent has an asymptote. Sorry, the degree of the numerator is less than the degree of the denominator, so a horizontal asymptote is the x-axis, or y equals 0. Label that. All right. For b, looking at the degree of my numerator is 2. The degree of my denominator is 2. Remember, the degree comes from the highest power on any variable in the polynomial. So in this case, the degree of the numerator equals the degree of the denominator. So the horizontal asymptote is the leading coefficient of p over the leading coefficient of q. So in the numerator, my leading coefficient is 2 because I'm taking, sorry, let me label my work. Horizontal asymptotes are y equals lines. So in the numerator, the coefficient of my one term there is 2. In the denominator, my leading coefficient is 1. So my horizontal asymptote is in the line y equals 2. Finally, my last example, the degree of my numerator is 2. The degree of my denominator is 1. So this is the case where the degree of the numerator is greater than the degree of the denominator, so there's no horizontal asymptote. All right, so now we're going to take a look at if there are any holes in a function. Remember, a hole occurs when you have a common factor in the numerator and denominator that will cancel out. It's part of the restricted domain. X cannot equal 3 in this case. So I'm going to throw the domain down here just as a reminder. But when I factor my numerator, it ends up canceling. Which means there is a hole in the graph at x equals 3 as opposed to a vertical asymptote like we saw earlier. Alright, so let's take a look at our next example. When I factor my denominator, I get what multiplies to -8 and adds to +2. So again, I'm getting this common factor in the numerator and denominator. So the hole occurs at x equals -4. And finally, we're going to put all of this information together. So start with the domain. Oops. So remember, our restricted domain is where the denominator is equal to 0. So in this case, x cannot equal +1. No, we don't know yet if that's a vertical asymptote or a hole. So we're going to take a look at the numerator to see if it factors out. In my numerator, I can factor out 4. Since that x minus 1 is not a common factor, this will be a vertical asymptote. Horizontal asymptotes, we need to look at the degree. In this case, let me rewrite it quick. The degree of my numerator is 1. The degree of my denominator is 1. And when the degrees are equal to each other, that's when we take a look at the leading coefficients. So the leading coefficient of my numerator is 4. The leading coefficient of my denominator is 1, so my horizontal asymptote is at y equals 4. So let me just make sure I'm getting everything. Domain, zeros. Zeros occur where the numerator is equal to 0. I factored my numerator. Since 4 will never equal 0, I'm going to set x minus 3 equal to 0. So the 0 of my function is x equals 3. And we covered everything else. Alright, so last example, starting with restricted domain. Again, in this case, my restricted domain is x cannot equal 1. Checking to see if it's a vertical asymptote or a whole, I'm going to factor my numerator. What multiplies to negative 15 adds to positive 2 will be a plus 5, negative 3. Since that x minus 1 doesn't cancel again, that will be a vertical asymptote. The zeros of the function are where the numerator is equal to 0. So I set x plus 5 equal to 0 and x minus 3 equal to 0. So the zeros of my function are negative 5 and positive 3. And then finally checking for horizontal asymptotes. So we look at the degree of the function. Looking at my original function, the highest power in my numerator is 2. The highest power in my denominator is 1. And when the degree of the numerator is greater than the degree of the denominator, let me double check myself and make sure I'm doing this right. The degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So, none. All right. Tomorrow in class, we will take a look at, I'll kind of show you what the sketch looks like based on this information. Again, it's not going to be real accurate because there are also things, there's a slant asymptote, which we haven't looked at, but we can have a general idea of what these functions look like. So in case you are watching this video as a makeup, there is the assignment. I believe I also have the assignment posted on ClassJump as well. Otherwise, we will see you tomorrow.